NASA unveiling a stunning new image of space.
I mean, I'm still just amazed at these pictures that came from the newly deployed James Webb Telescope.
The void of space is seldom silent, but the James Webb Space Telescope has pierced deeper into darkness than ever before, and what it uncovered is nothing short of haunting. Tucked between galaxies, beyond the familiar constellations, it spotted a colossal, enigmatic object that defies classification. It looms there, distant and inscrutable, glowing faintly, terrifying in its mystery, not by aggression but by sheer defiance of what we thought we knew about the cosmos. Before we start, smash the like and subscribe buttons for more updates. This object drifts where nothing compelling should exist, in the emptiness between galactic structures. It barely emits in ordinary wavelengths, resisting the full attention of Webb's sensors. Only in certain infrared bands does it flicker, a ghostly whisper in the vast dark. Its spectrum is perplexing. It lacks the fingerprints of stars or gas clouds, no obvious emission lines, no clear signs of nuclear fusion or heated dust. It seems more like an absence than a presence, a void that strangely radiates. To call it terrifying might suggest some malevolent intent, though it harbors no motive. The terror lies in what it reveals: nature's capacity to hide things far more exotic than we have imagined. Astronomers debate many possibilities. Some propose it could be an ultra-distant galaxy so old and redshifted that nearly all its light has been shifted beyond expectation. Others suggest it might be a so-called rogue object, an intergalactic wanderer, perhaps even a primordial black hole cloaked in dust, so dense that little light escapes. Another hypothesis holds that it may represent a transitional class, something intermediate between black holes, brown dwarfs, and dark matter halos, something we have not yet learned to define. None of these proposals fit neatly, and each raises more questions than it resolves. One of the most unsettling possibilities is that this object might belong to an entirely new class of cosmic structures, dark bodies that are not stars, not galaxies, nor even black holes in the usual sense. If Webb is glimpsing just the faint signal of gravitational interactions, perhaps we are seeing the outer edges of a structure held together by dark matter, or a concentration of exotic particle physics at cosmic scales. If that is the case, the discovery could be the first of many such shadows drifting through space, invisible to all but the most sensitive instruments. The implications extend far beyond mere curiosity. If objects like this exist more abundantly than we realize, then our maps of the universe, its mass distribution, its dynamics, its law of formation, are incomplete in fundamental ways. The gravitational pull of unseen masses could warp local motion in galaxies, tweak orbital paths, alter cosmic expansion in subtle ways. Dark matter models, cosmological simulations, even our estimates of how structure formed after the Big Bang may require revision. Where we once believed space to be sparsely populated, perhaps it is threaded by invisible filaments of objects lurking in the dark. There is also the chilling thought that if something so massive and anomalous can hide so well, then the universe could harbor other surprises, waiting just beyond the threshold of detectability. Perhaps among the countless patches of sky considered empty, there are dozens, hundreds, even thousands of such phantom entities, too faint or too cloaked to reveal themselves in conventional surveys. The Webb detection could be the first spotlight turned toward them, a wake-up call that the cosmos is far more hidden than we assumed. From the vantage of physics, the presence of this object challenges the boundary between the known and the unknown. If it is a black hole enveloped in dust, then how did such a shroud remain stable without being torn apart by tidal forces or dissipated by radiation pressure? If instead it is a relic from the early universe, a seed object left behind by primordial fluctuations, then theories of early structure formation must account for survivors so untouched over eons. And if it is instead made of exotic matter or dark sector phenomena, we may be glimpsing the first tangible hint of physics beyond the standard model. Even its location is provocative. It lies in a region between galaxies, not in a dense cluster or active galactic nucleus. That suggests it is not the ejected remnant of a galactic collision or merger. It is not being fed by nearby gas nor shining from accretion. It simply drifts. That solitude heightens its mystery. Nothing obvious feeds it. Nothing obvious shines through it. That isolation may be precisely what allowed it to survive, unperturbed, for billions of years. Webb's instruments, especially the infrared spectrograph and deep field imager, were crucial in detecting this object. Their sensitivity to faint heat signatures, the ability to look through cosmic dust, and the ability to peer deeper than Hubble ever could helped lift this whisper of an object from the background. But even Webb's power strains at the edges of detectability. The signal is weak, the noise high, and astronomers must carefully distinguish it from artifacts or background noise. But repeated observations have confirmed its persistence, its consistency across epochs, and its resistance to being dismissed. Observers are already planning follow-ups using multiple wavelengths, from submillimeter arrays to X-ray deep field explorations, to see whether there is even the faintest high-energy emission, perhaps from hidden accretion or particle interactions. Gravitational lensing studies may help measure its mass, by detecting how it distorts light from more distant background sources. If that distortion reveals a mass far higher than inferred from its faint light, it will confirm the presence of substantial invisible matter. Even gravitational wave observatories might someday detect perturbations from it if it interacts with passing objects. Through this discovery, a profound lesson emerges. The night sky is not the full story. We may have charted stars and galaxies with increasing precision, but for every beacon we see, there may lie hidden structures we cannot yet sense. The universe is deeper, not just in distance, but in substance, in complexity, in surprise, and in those unseen depths lie the next revolutions of astrophysics. At its core, what Webb revealed is a riddle. Why does it exist? What is it made of? How long has it survived? And how common is it? The search for answers will define a new frontier. If we succeed, our understanding of cosmic architecture, dark matter, and the evolution of structure will deepen dramatically. If we fail, we may be forced to accept that the universe is more unknowable than even our boldest theories allowed, and that perhaps is the greatest terror in all, that space holds truths beyond the reach of our most brilliant eyes. It becomes clear as one ponders this discovery that the cosmic theater is far more strange than our familiar acts of stars and galaxies. This new object does not behave like anything in the classical playbook. No swirling disk of gas, no powerful jets, no telltale pulses. It is a silent actor, lurking in obscurity. But silence in space can be the loudest signal of all. The faint emission Webb detected seems to come from thermal processes at extremely low temperatures. Its spectral energy distribution peaks in a region where cold dust and molecular gas might glow. But there is remarkably little indication of molecules. Carbon monoxide, water vapor, hydrogen lines, none show up significantly. If there is gas, it is extremely cold and diffuse or composed of molecules not yet considered. Perhaps the environment is so rarefied that collisions between particles are almost non-existent, making excitation of common spectral lines inefficient. That environment would be an ultra-cold vacuum, punctuated by a phantom glow from quantum or exotic processes. If we assume the object has some mass, assessing that mass becomes a delicate exercise. Gravitational lensing is one of the few direct tools available. Researchers will look for the faint bending of light from even more distant galaxies behind it. If those background sources appear slightly magnified or distorted, that distortion can be used to infer mass, but the lensing signature would be faint and subtle. In many cases, objects of modest mass, say tens to hundreds of thousands of solar masses, would produce distortions only at the limits of detection. If, however, the lensing suggests far more mass than can be accounted for by its detected emission, that would point squarely toward the presence of large amounts of unseen matter, possibly dark matter concentrated in exotic ways. Another method involves dynamics. If stars or galaxies near its location show unexpected motions, slight deviations, anomalous velocities, those might betray its influence. But since this object sits far from dense cosmic neighborhoods, there may be few or no luminous test particles near enough to reveal its gravitational tug. The isolation that makes it mysterious also shields it from easy measurement. Perhaps a more dramatic method would come from detecting subtle perturbations in the cosmic microwave background radiation, slight fluctuations or anisotropies that correlate with the object's position. If the phantom object corresponds to a mass concentration sufficient to gravitationally influence the last photons from recombination, it might leave an imprint in the CMB lensing map. That would be a bold and delicate measurement. But if captured, it would confirm that this object existed even billions of years ago, imprinting itself on the early radiation field. The possibility that this object is primordial in origin is especially tantalizing. Perhaps in the earliest epochs of the universe, during inflation, reheating, and the first moments of structure formation, density fluctuations of exotic form allowed the formation of primordial black holes or dense seeds of matter that survived the cosmic expansion. Those seeds might drift unnoticed through space, without accreting gas, or growing like the black holes in galactic centers. If so, then this discovery is the first concrete evidence of relics from the era before galaxies formed. That would shake cosmology at its core, forcing theorists to incorporate new mechanisms of survival and stability across cosmic time. One could imagine that many such seed objects exist, scattered across the vast intergalactic voids. Some might be entirely invisible, detected only via gravitational effects. Others might carry slight heat, perhaps from slow particle decay or dark sector interactions. Webb may have stumbled upon one of the warmest among them, warm only in the sense of still producing a whisper of emission detectable above background. Others might lie dormant, completely dark, epitaphs of the primordial universe. If multiple such objects are found, a population census becomes possible. Are they rare anomalies, relics of chaotic early times, or are they common, constituting a component of the missing mass of the universe? The latter would be especially transformative. It would mean that dark matter does not exist solely as a diffuse halo, but perhaps partly as compact, invisible bodies. Many existing models assume dark matter is smoothly distributed or clumpy on halo scales, but not in compact objects of measurable mass. A discovery of a population of such bodies would drive theorists to reconsider the nature of dark matter. Could it coalesce, fragment, or collapse under certain conditions? Does it interact weakly with itself to form bound structures? The boundaries between particle physics, cosmology, and astrophysics would shift. Another chain of inquiry regards energy emission mechanisms. What makes this object shine faintly in the infrared? If there is no accretion heating, then perhaps there are internal processes, such as radioactive decay of heavy elements or exotic decay of dark sector particles or low-level annihilation. There might be heat from capture of interstellar particles, cosmic rays, or dark matter interactions. Each of these mechanisms would leave a distinct signature in the spectrum, though extremely subtle. Disentangling such a signature will require long integration times, repeated observations, and perhaps novel instrumentation. Given the eeriness of its faint glow, some researchers contemplate quantum mechanical or exotic physics origins. Perhaps it is a region where vacuum fluctuations become semi-stable structures, or a concentration of vacuum energy fluctuations trapped in a potential well. That breaches into speculative territory, but one cannot rule out the strange in the face of the unknown. If nature supports vacuum-induced quasi-stable objects, their detection with Webb could herald a new class of quantum astrophysical bodies. Spectral anomalies already hint at unexpected absorption features, tiny depressions in flux at specific infrared wavelengths. These may correspond to unknown molecular species or absorption by exotic dust grains with unusual composition. Perhaps grains made of heavy cold metals or silicates altered by long cosmic exposure or composite materials formed under extreme conditions. The idea of dust becomes broader. It may include cold clumps of particles bound by dark matter halos, acting as mixed dark baryonic assemblies. One major question: why has nothing as massive been detected in prior surveys? Radio, X-ray, gamma, ultraviolet, optical, sub-millimeter all have scoured the skies exhaustively. The fact this object eluded all but Webb suggests its emission is extremely faint, perhaps peaking in narrow, unexpected bands or being masked by intervening absorption. This shows the limitations of prior telescopes and surveys. We have viewed the universe through many filters, but perhaps crucial windows remained closed. Webb has opened one of them. The region of sky containing the object will become a prime target. Observatories spanning the electromagnetic spectrum will collaborate. ALMA will probe sub-millimeter, seeking faint continuum or line emission. X-ray observatories may search for hint of high-energy processes. Radio telescopes might search for synchrotron emission, though none is expected, unless there is a hidden magnetosphere or relativistic particles trapped in a weak field. Next-generation instruments like the Origin Space Telescope or future infrared observatories will aim to peer deeper, with finer spectral resolution and better sensitivity. As more data accumulates, modeling efforts will intensify. Simulations of primordial structure formation must be updated to allow for compact relics that survive undisturbed by tidal disruption or mergers. Theories of dark matter itself may be tested, whether dark matter is purely non-interacting or whether slight self-interactions allow collapse into bound bodies. New parameter spaces will be explored: mass, cross-section, cooling mechanisms, stability. If even one of those new objects reveals a mass scale significantly different from expectations, it could break open entire swaths of parameter space once thought closed. Also intriguing is whether such an object might capture or accumulate material over cosmic time, albeit very slowly. Maybe tiny amounts of gas or dust drift into its gravitational reach, heating upon infall, producing micro-emission. That slow feeding might sustain a faint glow indefinitely, even in isolation. Alternatively, perhaps rare encounters with small interstellar clouds or dark matter streams inject energy, producing episodic flashes or flares. Monitoring over many years may reveal variability, minute fluctuations in brightness that betray unseen processes at work. If variability is found, that adds a temporal dimension to the mystery, a body that is neither star nor galaxy but pulses or flickers faintly as it interacts. That would be profoundly unexpected and might reveal physical processes far more exotic than simple cooling or passive emission. One must consider the cosmological context. This object lies at an enormous redshift, meaning we are seeing it as it was long ago. If light from it has traveled billions of years before reaching us, then the conditions under which it existed might reflect early cosmic history. Perhaps we are seeing it during a transitional epoch, before the universe became dominated by large-scale structure, or during a phase when exotic relics still glowed faintly. If so, then such objects might have faded further over cosmic time, making them nearly undetectable today. Webb might have caught one near its detectable window, a fleeting glimpse as it dims past the threshold of observability. That raises a temporal selection effect. We may only see those relics whose emission has not yet faded entirely. There may have been hundreds more early on, but only a few survive bright enough to observe now. That in turn means that the one Webb spotted may be a tip of the iceberg, the relatively rare survivors. The dark objects that are colder, older, or more isolated may remain invisible, even to Webb. If the object has a sizable dark matter halo, it raises the idea that what we normally think of as dark matter halos in galaxies and clusters might hide substructures, compact cores embedded within. Those cores might have condensed baryons, perhaps minute amounts of hydrogen or helium, which over time radiate faintly. So the boundary between galaxy-scale halos and these tiny relics could blur. They might represent the small end tail of halo distribution, the microhalos of structure formation. Detecting those would profoundly change our understanding of how structure is distributed on the smallest scales. The community will engage in cross-checking. Other deep field surveys will be recast to examine whether similar faint anomalies were hidden in their data. Archival data might hide weak excesses masked by noise. Perhaps in the James Webb archival fields, a systematic search for faint residuals near the detection threshold may reveal more such hints. In the same way that the first exoplanets were later found in archival radial velocity data once you knew the signature to look for, so too might these dark objects be hiding in plain sight, overlooked because they were too subtle. Moreover, theoretical distance estimates will play a major role. Redshift measurement of this object is tricky because its faint emission lines may not be resolvable. Photometric redshift derivation might provide a range, but uncertainty is large. If the redshift is extremely high, that places the object deep in cosmic time, so we would be seeing it as it was billions of years ago. That implies survival across eons, stability over cosmic expansion, and immunity to tidal disruption by galaxies. If instead the redshift is more modest, the object might reside in the nearer universe, making it easier to measure its environment and possible interaction. Pinning redshift is essential. Another question: is this object unique or part of a class? The existential loneliness we imagine may be illusory. Once astronomers know what to look for, they may uncover dozens more. The first detection may be the most visible, but others might cluster along lines in low-density regions or near galaxy groups. Some might be found at the edges of cosmic voids, in filaments rarely populated by galaxies. Others may lie near galaxy clusters, their presence masked by brighter neighbors. A survey focused on void interiors might become a new frontier, probing not for luminous galaxies, but for phantom masses. This sort of discovery also pressures instrument design. Future telescopes may require even greater sensitivity in faint infrared and mid-infrared, better suppression of background noise, longer integration times, and improved spectral discrimination to dig out weak signatures. Interferometric techniques may be applied to push resolution and sensitivity. Adaptive optics for space, coronagraphs for diffuse emission, or nulling interferometers might play roles. The drive to detect the undetectable becomes concrete. Philosophically, the presence of such an object reminds us of cosmic humility. Between the stars and the galaxies we see, vast dark realms may hide untold complexity. To regard the night sky as a map of all that exists would be hubris. Instead, we must accept that what we detect is only part of the story. The rest lies in the dark, waiting for better eyes and bolder hypotheses. One of the more profound implications touches on the cosmic inventory of mass and energy. Astronomers estimate the densities of baryonic matter, and dark energy through surveys of large-scale structure, gravitational lensing, galaxy rotations, and cosmic microwave background measurements. But if significant mass resides in compact, faint objects not included in existing catalogs, then those mass estimates might need adjustment. The dark matter fraction might partly be sequestered in these compact relics, not distributed smoothly. The missing baryons problem, wherein observed baryons fall short of predicted numbers, might find a partial home in cold, faint bodies. Perhaps some baryonic material, cooled and condensed long ago, has drifted into compact dark reservoirs rather than residing in diffuse hot halos or intergalactic gas. If so, the inventory of the cosmic baryon budget must be reevaluated. The discovery also weighs heavily on unification theories. Many theories of physics beyond the standard model predict the existence of hidden sectors, heavy, weakly interacting particles, or new symmetries that might produce bound states. The detection of an object that emits only faint infrared and exhibits no conventional signatures could be one of the first macroscopic manifestations of such hidden sector physics. In particular, if dark matter particles self-interact weakly, forming bound states or cooling via dark photons, then those bound states could gradually collapse, mimicking the collapse of baryonic gas into stars, but with dark sector analogs. Such collapse could produce compact dark stars or dark black holes that remain invisible or nearly so, detectable only by gravitational influence or weak emission. This object could be the progenitor of that class. The detection also provokes questions of cosmic stability. How stable is this body? What prevents it from collapsing, dissipating, or accreting away? If it is massive, why has it not tidally disrupted or been consumed by larger structures? Perhaps it lies in an especially quiet region, far from perturbations, or perhaps its internal structure is self-supporting, with pressure-like forces from exotic matter or degeneracy pressure. Or perhaps it is in a metastable state, a long-lived but not eternal structure. If metastable, it may slowly decay or collapse over cosmic time, meaning similar objects might fade or vanish. That raises the possibility that the observable population is time-limited, making each detection precious. The fact that Webb could detect it also invites speculation about how many other cosmic mysteries might await discovery by future, more sensitive telescopes. If a single phantom object has evaded detection until now, there may be countless others in black corners of parameter space. Objects with strange spectral signatures, extremely cold, extremely quiet, lurking beyond the reach of classical survey strategies. The initiative to explore the infrared frontier, the unknown middle band between cold dust and zero temperature, becomes ever more vital. The universe might host a hidden zoo of dark relics waiting discovery. As astronomers pore over the data, debates will rage. Is this detection real, or a trick of instrumentation, a ghost of cosmic noise? Only reproducibility, multiple instruments, multi-wavelength confirmation will calm skepticism. But if solid, this moment marks a turning point. Our cosmic census must expand. New classes of objects may percolate into textbooks that previously cataloged only stars, planets, galaxies, black holes, and nebulae. The taxonomy of the cosmos may widen, adding entries for dark relics, invisible microhalos, dark sector bodies, or cold phantom masses. Our classification schemes may evolve to include not just the bright and visible, but the faint and hidden. Yet the terror in this discovery is not horror, but wonder. It is the sense that nature continues to surprise, to conceal, to tease us with shapes and forces we have not yet named. Each generation of telescopes peels back a new layer of the cosmic onion, and still more lies beneath. The James Webb Space Telescope has shown us that even the emptiest-looking stretches of sky may harbor unexpected wonders. There is more to space than meets the eye. Astronomers will set in motion proposals to map regions of cosmic voids with deep, high-sensitivity observations, specifically targeting the kinds of spectral windows in which this object glows. They will allocate time to chase potential sisters. They will propose instrumentation optimized for extremely low surface brightness, pushing technical boundaries of detector noise, background subtraction, stray light suppression. The drive will shift from seeing the bright to seeing the faint, from cataloging what shines to cataloging what barely whispers. The attempt to understand this object will also refine our understanding of astrophysical limits. We will test the thresholds of detection, the floor of brightness, the edge of noise. The boundary between detection and non-detection becomes a frontier line. Where is the threshold at which objects remain forever invisible, even to our most sensitive tools? What is the fundamental faintness limit in cosmic observation, set by backgrounds, instrument noise, and cosmic interference? This discovery pushes us to refine those limits and reconsider how much of the universe lies below them. In the public imagination, a terrifying object in space evokes monsters, collisions, or imminent threats. But this object is terrifying not for danger, but for its reminder of cosmic ignorance. It reminds us how much is still unknown, how much may lurk unseen, how many cosmic shadows await discovery. It challenges our confidence that we have cataloged the major components of the universe. It forces humility. At a deeper level, this find touches on the philosophical boundaries of knowledge. How far can we probe? Will there always be regions beyond reach, objects that produce signals too faint, too diffuse, too exotic for our senses? Are there elements of reality that remain forever hidden? Not because we lack better telescopes, but because nature conceals them behind principles we have yet to discover? This phantom object, drifting between galaxies, invites us to reflect on the limits of observation and the nature of what is knowable. Looking ahead, the pace of discovery will likely accelerate. With more powerful instruments, better processing, and refined search strategies, more phantom objects may be uncovered. Each new detection will refine the parameters of possible theories, eliminating shaky models, positing new ones, and gradually filling in the dark corners of cosmic inventory. Over the coming decades, this track could become as robust as the search for exoplanets, with catalogs of dark relic bodies stretching across volumes. One day, perhaps, a network of such objects may reveal a larger structure, an unseen web of dark bodies threading through cosmic voids. Perhaps they trace an invisible scaffold underlying visible structure, linking filaments and voids with a hidden architecture. That hidden architecture might guide galaxy formation or subtly influence dark matter distributions. In that case, galaxies and clusters that we see might form around this invisible skeleton. The map of the universe we know, made from luminous matter, could turn out to be only part of the picture. The deeper map, of hidden mass, may underlie everything. If one of these objects lies close enough, it might even offer opportunities for direct gravitational interaction studies. Perhaps a passing star, cloud, or even spacecraft might perturb or interact with it. Such encounters would offer more concrete probes of structure, mass distribution, gravitational potential, and internal properties. Of course, a close approach is unlikely in human timescales, but even the thought invites possibility. In the decades to come, perhaps successor telescopes, optimized for ultra-faint detection and precise gravitational mapping, will explore entire swaths of space searching for these dark relics. Perhaps a mission will be designed specifically to search for faint lensing distortions rather than luminous sources, scanning empty regions to reconstruct maps of invisible mass. Imagine a telescope whose purpose is not to see what shines, but to map the silent gravity footprints of hidden bodies. What this discovery ultimately shows is that discovery rarely proceeds in smooth progression. Sometimes it comes as a disruption, peeling open a new area of inquiry. The object Webb detected is more than a curiosity. It is a line drawn across expectation, challenging long-held assumptions. The aftershocks of its discovery will resonate across astrophysics, cosmology, particle physics, instrument design, and philosophy of science. This silent wanderer also prompts reflection on our place in the universe. We often feel small in cosmic scale, dwarfed by stars, systems, galaxies. But to think that even in the spaces we consider empty, there are phantom giants we have not yet seen, that is a humbling revelation. The solitude of our vantage point, the narrowness of our senses, the blind spots in our surveys all become more evident. So the story continues, not as aftershock, not as reaction, but as unfolding inquiry. This object sits out there, distant and inscrutable, a challenge and an invitation. It implores questions. What is the nature of matter and dark matter? How do structures form and survive? How many cosmic relics drift hidden? What limits our ability to see them? How can we design future instruments to peer deeper? The journey ahead lies in chasing the faint, mapping the unseen, exploring the silence of the void. In the silence of deep space, the James Webb Space Telescope has heard a whisper. That whisper is the presence of something uncanny, something beyond present classification, something that provokes wonder and dread. The implications ripple outward. Our cosmic census must expand. Our theories must adapt. Our instruments must evolve. This is a turning point. The phantom object is not a threat, but a revelation, a portent of the hidden depths of the universe, and an invitation to explore them. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what the James Webb Telescope just detected in deep space? We want to hear from you. Thank you for watching, and see you next time.